first equation over there, x squared plus 18x plus c. I am asking you to give me the c, so you're allowed to put there whatever you want. But my request is whatever you figure out for c needs to make this trinomial a perfect square. Meaning not only will that trinomial factor, but it will factor into something squared. Two of the exact same factors. Okay, Marcus?
4.5 times 4.5.
I don't think we need to do 4.5 times 4.5. That will give us a decimal. This one doesn't have to be a decimal. Think if there were two of the exact same things, what do you know is at the beginning of each of them if it's made x squared plus 18x plus some constant that you're allowed to pick? X. Okay? So that would make x squared, right? And if these are two of the exact same thing, you know that when you do this multiplication and this multiplication, you'll make two middle terms that each have an x with them, right? But it's supposed to be two of the exact same thing. So what should be here if I'm supposed to build 18x in the middle? Brandon? Okay, good. Yeah, good. 9 here, right? Because 9 plus 9 would make 18, okay? Which means that forces the number at the end of the polynomial to be 81 now. So the fact that we only have the middle number of 18 forces these to be 9s, which then tells me the last number has to be 81. That's the only way to make this setup a perfect square. Does that make sense to everybody? Okay, so it gets a little more complicated when we look at something with like 9 in the middle. So we like to kind of generalize this into a formula. So what's going to happen every time that we go to do this? What are we going to have to do every time? If they're giving us the beginning term, they're giving us the middle term, and we want to figure out the number to put at the end to make sure it factors as a perfect square. What are we going to do every time? Okay, so divide the middle by 2, right? Because it gets split up into these two exact same things that had to add to it and be that. Okay, so the middle coefficient we call b normally. So we're taking b and dividing it by 2. That gives us these numbers. Then what do we do to that to get the number that should be at the end of the polynomial as our constant? Here? Good, we square it. This is the formula for completing the square. So you can put a little bubble around it, highlight it, whatever you like to do to it in your notes. This is kind of our shortcut formula instead of having to think through that process every single time for completing the square. Now, if you forgot it, could you figure it out? You guys just figured it out right here, right? Without a formula. You have brains and math power. You guys can figure it out, okay? But the formula makes it faster for us. So now when we look at something like 9, that mind boggles us a little bit more because it's not as easy to split in half as far as nice whole round numbers. We look at 9. If we were to take negative 9 and divide it by 2, we would get a fraction. We're going to leave it in fraction form. Okay, I know. It sucks. Get used to it. It's okay. Negative 9 over 2, and then we square it. What is that constant that should be at the end there? Marcus?
81 over 4.
Good. 81 over 4. Is this all right with everybody? Okay, now the last one is up here because it gets a little bit tricky. It is not 81. Okay. It is, why wouldn't it be 81 if part A was 81? Gabby? Good, because of the 2 in front of the r squared. Our little rule here only works when we already know how exactly to split up that front perfect square. So we need to get the 2 out of the polynomial so we can use our normal reasoning, and then we can decide if we want the 2 back in or not. So for this problem, we need to think of factoring the 2 out. Okay. And then we can figure out what goes here. Now, what goes here is not the same as what goes up there for C. That's why I specifically didn't write C, right? Because the C has the 2 factored in. We just took the 2 out. So I'm trying to be careful not to call it the same thing because it's not the same thing. But we can do this problem. If this coefficient here is negative 9, we already figured out what number is supposed to be put at the end of this polynomial. Look at part B. 81 over 4, right? If you take negative 9, divide it by 2 and square it, we'll get 81 over 4. So the number that completes this and makes this a perfect square is 81 over 4. No, because we square it. So even though the middle term is negative, when you complete the square, the last ones will always be positive. Because remember, you're trying to make it so it factors as two of the exact same things, which means they're either both negative or both positive. Each time multiplying those would give you a positive constant. Marcus?
I got 2r minus 6.
Okay, so we're trying to rewrite part of it though as a perfect square. So we couldn't do that with 2. If we use 2, we're not going to have a perfect square unless we use rad 2 in it. So that's why we separated the 2 out. Okay? I'm only going to put it back in, which everything else should look the same as it was, to see what the number was that they want C to be in this problem. So 2 times 81 over 4 would give me 81 over 2. So 81 over 2 should be the C value here if I want to create a perfect square. Okay? Not factoring it otherwise, just to create a perfect square here. Mm-hmm. You can't reduce it that way because you're taking square roots of top and bottom. Remember, you could, okay, so you could make it, no, you can't because 81 is not divisible by 2. But let's say it was like 18 over 4. Then you could call it like 9 over 2 if they were both divisible by 2, and it's fine to reduce it. But it will be helpful, as I'll show you in the next couple problems. It's actually easier to not reduce it till the very end. Because remember, you're making a perfect square. Why do we like perfect squares? How did you guys solve a bunch of the problems that you just did? When there was perfect squares, you took square roots, right? So if something has like a 4 in the denominator, I don't really want to reduce it because if later on I'm going to take the square root, 4 is a really good number to have in the denominator. So my advice if you're using this process would be to not reduce till the very end. Okay? All right, so this was to get the idea. So here's how we use the idea. So one way we use the idea is by solving problems. So I know that this is factorable and it's really super factorable, and on your test you will get to choose to solve however you want. Okay? So I will not be like, oh, it's so easy and factorable, but you have to use completing the square. But I want to show you an example of how to do completing the square. So we're going to do this really easily factorable problem by completing the square here and in this section just to practice completing the square. By the time we get to the end, you guys have choice. Quadratic formula, completing the square, factoring, totally up to you. But I need to get you to a place where I know you can do all of them, and you're just choosing what works best for the situation. So we're going to force you to do it right now, but at the end, you'll be informed enough to use whatever method works well for the problem. Okay? So if I was going to solve this by completing the square, it has to factor and be a perfect square. Right now, x squared plus 2x minus 120 factors. We already know, we're putting that aside. But does it factor as a perfect square? No. Okay? So what I want to do is like 120 is not the number I want there for it to be a perfect square. So I'm actually going to remove 120 to the other side of the equation and act like it's not part of my polynomial. And I'm going to choose a different constant to be in its place. I can do this because it's an equation, right? I can add anything I want to one side as long as I also add it to the other. So if I don't want the 120 to be there, I add 120 to both sides of my equation, and I get this equation. Again, why would I choose to do that? I probably wouldn't. Given choice in this situation, I would just factor. But if I was trying to make a perfect square, 120 is not the perfect square number I want. Okay? Now, I want to choose a number here that with this polynomial makes it factor as a perfect square. In other words, I want to complete the square, right? So what value do I want to add here at this polynomial to do that? Marcus? 100. Not 100. Rasmus? Just 1. So we have x squared plus 2x plus 1. Remember, we take the b term, we divide it by 2, and we square it. So if I take 2 out, I divide it by 2, and I square it, that's going to give me 1. I'm going to write it in different colors so you know that I chose to add it there. So I am choosing. I am putting something new into this problem. I would like a positive 1 here, which is totally not okay in mathematics for you to just change the problem the way you want. But if it's an equation, it's totally okay for me to put a 1 there as long as the other side gets increased by 1 as well. Right? So it's completely okay for me to put anything I want here as long as the same operation is done on the other side. So on the right side, that's 121. I now know this should factor as a perfect square. If you've completed the square and you're like, I don't know what to do next, there's one reason why you completed the square, to make a perfect square. So if you are at a process where you're doing something and you completed the square, your next step should be to write it as a perfect square. Okay, so what does this factor as far as perfect squares? X plus 1. And now I could solve it using square roots. So I square root both sides. I get x plus 1 here. I get both positive and negative 11 here. Okay, two choices. So I solve each of these options to explain the values that x could be. So x is 10. No, that's not right.
X plus 1. Negative 11 minus. Yeah. You put x minus
Yeah, thank you. All right. Good. So we could have got these answers much faster by factoring. I'm not saying completing square is the method to use at this moment. I'm just trying to give you examples of how to use it. So when the situation does arrive, you can. Okay? All right. So what would we do in part B if we wanted to solve this by completing the square? Yeah, Natalie? Okay, good. So I want to move the 12 to the other side, because 12 is not a perfect square. That's not going to factor as a perfect square as it is. And then did you guys hear what she said? Divide the whole equation by 2. Does our little completing the square trick work with any coefficient in front of x? No. So it doesn't even matter. It's like I might not want to divide by 2 because it's going to make a really ugly number right here. But I can't use this process unless the coefficient here is 1. The 2 can't be here. Okay? Otherwise, we can't split it up the way we did. That shortcut doesn't work. So if I divide everything on this side by 2 and everything on this side by 2, and now I'm going to complete the square. So you don't like it because it has a fraction, I already know. Okay, but we're going to get over it. We're going to deal with it. So I need to take negative 7 over 2, divide it by 2, and square it. Okay, so I'm taking this number, I am dividing it by 2, and I am squaring it. What is negative 7 over 2 divided by 2? Good, negative 7 over 4. Because remember, taking a fraction and dividing it by 2 is the same as taking the fraction and multiplying it by the reciprocal of 2. This is probably the most fractions I will ever write out for you. Okay, so get used to it. Yeah, so then this is going to be 49 over 16. So you might cringe. It doesn't matter. Just leave it like that. It looks ugly, but at least those numbers 16 is square rootable, right? Okay? So I'm going to add 49 over 16 to both sides. I'm going to have to make fractions your friends, okay? So remember, this should be a perfect square now, and then I'll add these things together. So here, how this should factor. X has to be at the beginning. What has to be at the end of the perfect square if it made 49 over 16? Something times itself that made 49 over 16. 7 over 4. You just did it. And then it has to make a negative coefficient in the middle, so this should be negative. Okay? On this side, I'm just going to make common denominators and add them together. So I'm going to think of it instead of 6 times 16, 36, negative 96 over 16. So when I add that to 49, I get negative 47 over 16. And what's going to happen here when you go to your next step and you go to square root it? I get x minus 7 over 4 equals, Natalie? Okay, but what about this? Okay, so we're just going to leave this where it is right now, and we'll say this for right now. No real solutions. We're going to find some solutions later. They're called imaginary ones or complex ones, but there aren't any real solutions to this problem. In the real number system, you cannot. Well, we're going to learn the complex number system in at the end of this week. It's going to be great. Don't worry. All right. Last way that we use this. So remember how I gave you guys the problem and I told you if you're super on top of how standard form and vertex form are related in the parts of the parabola, you could probably take any standard form and write it in vertex form without knowing completing the square. Okay, you can. There's a way. But completing the square is something that we use this for, and this is going to be useful next year when you do conic sections. So conic sections are sideways parabolas, ellipses, hyperbolas. You study, and circles, okay, which you've studied in geometry, right? Like the equation of a circle, like x squared plus y squared equals r squared kind of thing. But sometimes it's more complicated, like x minus 3 squared plus y minus 4 squared equals 16. Something like that. If you don't see it like that, if they have it all multiplied out, you have to be able to rewrite it in those perfect square groups to see where the center of your circle is and the radius and stuff like that. So that's what we want to do here. So what we would do is we know we need part to be a perfect square, and 27 is not the number to do it. So we're kind of like kicking 27 out of the group. You know how in the equations we subtracted it and moved it to the other side? You can do that right now. It'll say y minus 27 over here. But notice how it's kind of becoming like our k value. It's like out of the perfect square part, like a, h, k, because it can't make the perfect square. So I can add in, again, this is an equation. I can add in whatever I want here. What do I want to add into this equation? If I want to make a perfect square, I want to write it in vertex form. I want that perfect square root. 25. Okay, so we take 10, we divide it by 2 and square it. We decide we want 25. Now, I just changed the equation. What do I have to do to even that out so I haven't really changed the equation even though I wrote something new? So I either need to also add 25 to the other side, or if I don't want to put any numbers over here, what could I do on this side? Subtract 25. It's the same thing. All right, so my h is negative 5, my k is 2, my a is 1. Here's the equation in vertex form. Okay. Sucks a little bit when there's a coefficient, right? Because what's going to happen when there's a coefficient? Which means that coefficient is our a value, okay, which makes sense why the a value in standard form is the a value in vertex form, because we have to separate it. Now, notice I am not going to make the 10 a 5. Why did I not factor the 2 out of 10? Why does the 10 not say 5 now? Rasmus? Good. If I had factored, it would have to be in here. Do I want it to be in there? No, because it's not my perfect square number. Okay? Now, we already did the work for this in the last example up above it. Okay? 7 over 2 divided by 2 and squared gives us?
49.
Now, I wrote down the number 49 over 16, but how much did I really add to that side of the equation? Is 49 over 16 just 49 over 16? No, it's 49 over 16 being multiplied by 2. So I added 40, I wrote 49 over 16, but it was in parentheses being multiplied by 2. So it's really like I added 49 over 8. Why do I have to know that? Because when I go to even out what I just did to the equation, do I want to subtract 49 over 16 right here? No, I didn't really change it. I wrote that number, but that's not the quantity that I changed the equation by. I really changed it by 49 over 8. So that's what I would want to put here. Okay? So this then, there's my perfect square. Again, I know the fractions bug you, but they're not too bad here. The worst part is just adding together the pieces at the end, right? Making a common denominator. So 10 is like, if I want it over 8, it's like 80. And 80 minus 49 is 31. And there's my equation in vertex form. Anybody know how you could have gotten it in vertex form without using completing the square? If an equation's in standard form, how can you find the vertex? Negative b over 2a and plug it in. So if you do that with this, you'll get negative 7 over 4, comma, 31 over 8, and you'll have the vertex. And then how would you know what to put as the a value? The same a value. You can use completing the square. You cannot use completing the square. It might be faster, okay? Then why do we learn completing the square? Because in the future and in some circumstances here, it is better for us or easier for us or important for us to recognize something written one way as something that could be written a different way. Does that make sense to everybody? Okay, so tonight's homework, you might see problems that you're like, I know how to factor that. But it's trying to practice the skill of completing the square. So it will force you to use completing the square so that you get used to this idea. And then when you come in tomorrow, we're going to use completing the square to derive the quadratic formula. Okay? All right, any questions about this? So the homework that goes with this is homework number 6. Okay?